Hello, everybody. Welcome to our session. I have Frode and Nordahl with me today, and I'm Dmitrii Shcherbakov. We're both senior engineers on the OVN team at Canonical, and we'd like to talk to you about finding in the context of OVN and SmartNICs. SmartNICs are an overloaded term. There are different classifications, but we're going to talk about ASIC-based off-path SmartNICs. And just to illustrate what a SmartNIC is, you'll typically have a NIC switch in the off-path ASIC-based SmartNIC case. It's an ASIC that can be programmed via a data path such as OVS system data path integrated with OVSTC. And you have the OVN and OVS agents running on your host, and the host processes consuming VFs. It could be containers or virtual machines, and your PF driver would contain the switch dev capabilities so that the flows could be programmed into the switch. Compared to DPUs, you'll see that in the DPU case, there are no networking agents, and the PF driver doesn't expose the switch dev capability. You have an add-in card with its own CPU, RAM, its own kernel, and the PCI Express complex. And it can program flows to the NIC switch that hosts cannot. And it also runs the OVN and OVS agents, and effectively all of your control plane is at the DPU side and not at the host side. So I guess the key takeaways would be that it's an embedded system with its own components and a dedicated CPU that runs its own kernel. The NIC is integrated with the main board using some form of IO interconnect. It's in most cases it's PCI Express, and the NIC is shared between the dedicated CPU and the main board CPU, and those are two separate IO hierarchies. So addresses are the same on them, and they don't really see each other. The Offpath architecture has a couple of main traits. So you have the slow path, which is on the NIC cores, and you may have offloads configured there, which enables your fast path. So that would be the direct flow of packets to the destination that bypasses the NIC cores. And what are the challenges associated with using DPUs with current CMSs? Well, the current inference software expects the same host topology where networking agents run side by side with, let's say, the hypervisor agents. So you have a different host name, you have different PCI addresses, so you can't refer to the PFs, VFs, and their representers using the same set of PCI addresses as you would in the non-DPU case. You have to think about how to allocate VFs on the hypervisor, but consume and program them at the DPU side. You have to know how to map essentially the hypervisor itself to a particular DPU. And what if you have multiple DPUs per host? You have to think about that. And you need to think about how to maintain security boundary between the host and the DPU so that the host doesn't have direct code execution capabilities at the DPU. And you need to think about how to communicate between those two hosts securely. So the current gaps are that there is no sort of control plane for enabling those hosts to cooperate in order to get virtual functions programmed appropriately. So you can't do the remote plugging. There is no way to sort of map a hypervisor hostname to a particular chassis, or identify which VF refers to which GPU. And also OVN needs to be able to plug representers into OVS bridges based on logical switch port information, and traditionally it has been outside of its responsibility.
All right, let's talk a bit about our design goals when working on this. So we wanted to reuse as much of existing code as possible. When you think about it, the DPU case, although the topology is quite different, the components involved are the same as with the offload architecture. There are still VFs, there are still virtual machines, and it's open vSwitch that does the PC offload and things like that. We also wanted to be CMS agnostic because while we're implementing this in OpenStack first, because that's where we have the largest user base, it's also interesting for Kubernetes users and users of LXD. So this is one of the reasons why we want to have the API for creating the representative ports in OVN itself. The other reason is that a lot of these CMSs has a scalability and efficiency problem in their communication around the networking. So having OVN to do this communication, which is super efficient and secure with TLS, is a very good, has been a very good carrier for us. We also want to be as generic as possible when handling the devices and vendors. We use infrastructure that's generally available in the kernel. And we also want all of the things we do to be upstream first. We rely on existing upstream projects and APIs. And when possible, and there's not necessary to create, a new project for everything, we implement the features in existing software. As Dmitrii touched on in the previous slide, security is also paramount in this case. That's one of the main use cases for having a DPU in the first place. So we essentially want the data plane host to be treated as untrusted, and that's why we don't allow direct communication between the host that hosts the payloads and the DPU, which controls the host essentially. Let's go to the next slide.
So how do we implement all the discovery? Well, the problem is that virtual functions and physical functions in the case of an embedded switch are all virtual ports, and an identifier like MAC address is not really fit for use there. So we needed some alternative at the board level in order to implement this and make this as automatic as possible for a hypervisor to be able to send information to the DPU and for CMS to handle that. So apparently there is a PCI standard capability called VPD, and it has a board serial number in it. It is unique and read-only. It's assigned at the factory and exposed at FVPF and optionally at VFs if the firmware supports it. So the idea is that a hypervisor would supply some information about IVF or take the VPD information from a PF, and then the CMS would be able to do the lookup of a DPU that should service the port plugging request. And you might ask, whether PCI VPD is a supported thing. And at the next slide, we sort of gather some information about what VPD is. So it appeared in quite an old spec. Most modern NICs that we've encountered have it, and it's exposed in very ancient Linux kernels. So if you use a kernel today, you'll most likely have it exposed via SysFS. So it's a pretty reliable identifier for us to work with compared to say MAC addresses, which become blurry because they can be reprogrammed, or if you think about the burned-in MAC addresses, what is a burned-in MAC for virtual NIC switchboard? Well, it's not very reliable for this case, so the serial numbers serve us better.
All right, let's talk a bit about the work we have done in OVN so far. So in core OVN, we have added a VIF plug provider framework. What it provides is a CMS API, which relies on the existing requested chassis options. In addition, you can specify a plug type, which refers to a VIF plug provider implementation, and you can specify things such as the MTU that the representative port should get. What we've added in regards to the requested chassis option is that now it's actually written into the southbound database in a separate column, and this allows the OVN controller to subscribe to events on any port binding record which is destined for it, even before it has been bound. Without that, it would have to iterate over all the records, and that is of course not scalable. And each of the VIF plug provider implementations registers callback, so that OVN can focus on doing what it does best, reading and writing from the OVN databases and the local vSwitch database. And if we look at the OVN VIF side of things, we have created a separate project where we keep system and device specific code. It is hosted under OVN org on GitHub. And it's prepared to host multiple VIF plug provider implementations. We follow a GitHub PR-based workflow, so patches are welcome. Come participate with us. In there right now, there is a representer VIF plug implementation. It adds the following keys to the CMS API, which is the PFMAC and VF number. The PFMAC is added there because, say you get a DPU with multiple controllers. Even though you target the card with the serial number, you need the PFMAC in addition to that to know which one to find the right representative for. And so the existing implementation would support any SmartNIC DPU that uses the devlink port infrastructure. And in there's also a devlink library, which is based on the great Open vSwitch netting library code, which we can build on further. Yeah, let's look to the next one.
So here you can see how a typical CMS integration would look like. We have OpenStack and Kubernetes as specific examples here. And we've been working upstream in Nova, Neutron, libvirt, and OVN to make the necessary changes. You can see here that there are no CMS-specific agents at the DPU side, so the OVN code is applicable to different kinds of CMSs. So while we haven't addressed the necessary changes in Kubernetes, for example, this will happen in due course, and it will be applicable for different CMS projects. Let's talk about the high-level control flow in order to create an instance with a SmartNIC port. Before you do that, you need to have a chassis registered in the southbound database, and that chassis runs at the DPU side. You basically need to specify the port serial number in the configuration, and then the DPU hostname will be registered in the southbound database. Then you can start creating ports of VNIC type SmartNIC at the OpenStack side. You need to pre-create a port before you create an instance. So when you create an instance, you specify the pre-created port, and Nova will look for a node that can service a request based on the availability of virtual functions, which you specify in the configuration as well. Once it finds the right host, it starts building it, and in that process, it allocates a VF and updates the SmartNIC port with the VF details, which include the newly added board serial number, VF logical number, and the PFMAC. And Neutron then consumes this information and creates a logical switch port in OVN with the same information that OVN will understand. It will then send a bind time event to Nova so that it can pause the instance and continue with its creation. And the rest of it is at the OVN side.
Yeah, so when the CMS creates a logical switch port in the Northbound database, the Northd monitors this table and will notice new records. It will go through the records, and if there is a logical switch port with the requested chassis option, it will use that information to fill the southbound port binding table, and it will also fill the requested chassis column with the UID of the chassis. The chassis on the DPU side then will go over all of the port binding records which are destined to it by looking at the requested chassis column. If it finds a plug type option there, which corresponds to a plug provider implementation which has been compiled with, it will then use its callbacks to look up the representer port and use that information to create ports in the local Open vSwitch database. When creating a port, it also adds the interface ID so that the existing port binding code in OVN will find this port and create flows and bind the port, etc. Upstream status is that the OVN framework for the plug support is in OVN master now. It will appear in 21.12. We have also upstreamed the OVN diff project to OVN.org, and it will follow the release cadence and the release process or as OVN, so that will be available shortly. In OpenStack, we have specs merged for Nova and Neutron, and we have either work in progress or actual code under review, and we are committed to get this into Yoga.
And last but not least, if you have any devices that you would like to test this on, ping us on IRC or via email, and possibly send us a sample, because we could try this out in our labs and see if there are any device-specific things that we've missed. We've tried to keep this based on the standard APIs as much as possible, but things can work differently with complex devices such as SmartNICs. So having more devices to test on is definitely a good thing for us.
And we have prepared a quick demo, so let's go look at that. Let's start by deploying. We have two machines, one which will be the untrusted compute host, the other one will host the control plane services. Let's just let that fast forward a bit. And the second thing we will do is add a PPA, which contains the in-flight, not yet merged code. And what we will do next is to set up the number of virtual functions that we want to use on the compute host. And then we will use the Juju manual provider to add the actual SmartNIC control plane operating system to the model. Now that we have that, we can deploy OVN to it. And there we set the configuration for the serial number as we talked about in the presentation. If we SSH into the compute host, we see that there are Canonical agents. The field itself. See, this is an ARM device. And here we have OBS and OVN running. This is what the network configuration looks like. Let's create an instance. So this script here will create a port of VNIC type SmartNIC and a server. While that boots, we will look at the port. As you can see here, the serial number is populated, PCI slot, PCI vendor info, PFMAC, and the physical network is none here because this is a overlay network, and the VF number. As you can see, OVN controller has plugged the port. It has claimed the port and put the flows in as it usually does. And as you see, the instance has also already asked for DHCP. Okay, let's see if we can reach this. All right. As we can see, virtual function is visible inside the instance. Now let's see if we can have some traffic. You can also see the traffic is offloaded.
All right, I want to thank our speakers, and I believe that we have at least one of them available to answer questions. Welcome to the audio and video, Frode.
Hello, how are you? Can you hear me?
Yes, I can hear you just fine. So we have one question from the audience. It's from Flavio Fernandez, who asks, would OVN.org or OVN-VIF integrate with Neutron ML2 OVN, or is it essentially doing something similar?
So ML2 OVN is essentially the driver in OpenStack, which talks to OVN as a CMS, whereas OVN-VIF is a plugin that you plug into OVN itself to deal with hardware specifics of such as the Bluefield device, which several talks has been about today. So it serves a different purpose, but you would use both of them to deploy what we just saw here.
That's great. We also have a comment from Flavio who adds that doing what you're doing in a CMS and vendor agnostic way is not easy, and says, nice talk.
Thank you, Flavio. And since you have a few moments left, I would like to thank the OVN community for helping us getting this feature in with the reviews and everything. It has been a lot of work on our side, but I believe it has been a lot of work on your side too, to shape us into how you want code into OVN. So thank you.
That's great, and that's a nice note with praise all around to end this talk and this session. We now have a short break.